Imagine you're driving at night with the headlights off. No street lights, no signs, no phone signal. Now imagine you still have to arrive at an exact address, silently, without stopping. That is underwater navigation. A submarine lives inside a world that erases the tools we take for granted. GPS does not reach the deep. Radio signals fade fast, and the ocean offers almost no visible landmarks. Yet submarines still cross entire seas, thread through narrow corridors, and return home, often without ever being seen. So how do they know where they are, when the ocean gives them nothing? Today, we build the answer like engineers do, not with drama, with a model. Because in the silent ocean, navigation isn't a feature, it's survival. 1. 3 definitions we actually use. Let's define 3 terms in plain language, only what we need. An inertial navigation system, INS, uses internal sensors, gyroscopes and accelerometers to measure how you move, then calculates where you must be. Example: if the sub accelerates forward for 10 seconds, INS updates speed and position without looking outside. Dead reckoning means you start from a known location, then estimate your new position using heading, speed, and time. Example: we were here at 2 o'clock. We traveled this direction at this speed for 30 minutes, so we should be here. Bathymetry is the terrain of the ocean floor, ridges, slopes, canyons, like mountains and valleys but underwater. Example: a sub can compare measured depth patterns to a map and recognize where it is, like matching fingerprints. These 3 ideas will carry the whole episode. 2. Why underwater GPS isn't a thing. Let's make the problem concrete. GPS satellites send radio signals. Radio waves travel well through air, but not through seawater. Seawater is conductive. It absorbs and destroys most radio frequencies quickly. So a submarine has a choice: stay deep and blind to GPS, or rise close enough to the surface to receive something, which can expose it. This is why navigation underwater becomes an internal skill. The submarine must bring its own map, its own sense of motion, and its own error control. And that takes us to the core system. 3. INS, the submarine's inner ear. Think of INS like the balance system in your body. When you close your eyes and walk across a room, you can still estimate where you are. Not perfectly, but well enough. INS does the same thing with instruments. Gyroscopes track rotation, how the submarine turns. Accelerometers track acceleration, how speed changes. From acceleration you get velocity. From velocity you get position. It's basically this idea. Position is what you get when you keep adding up your motion over time. That's why INS is powerful. It does not need the ocean to cooperate. It does not need signals. It does not need visibility. It works in silence. But there is a catch, and it's the most important catch in navigation. 4. Drift, the silent enemy. INS is a calculator, and every calculator has error. Tiny sensor noise, minute calibration imperfections, a slight bias in a gyro, a small acceleration error. Each one is small, but INS integrates motion over time, meaning the errors accumulate. So the submarine doesn't just get a small mistake once, it gets a mistake that grows. This growth is called drift, a simple way to feel it. If your position estimate is off by a tiny fraction each minute, after hours you can be off by a lot. And a lot underwater can mean missing a safe corridor, arriving late to a rendezvous, or in worst cases, approaching the seafloor at the wrong depth. So submarines don't rely on INS alone, they rely on INS plus correction, and that gives us our episode's core model. 5. Model card. Measure, integrate, correct. Here's the model we'll use from now on. Measure. Track motion internally. Integrate. Convert that motion into an estimated position. Correct. Use occasional external clues to pull the estimate back toward reality. INS does measure and integrate, The art is correction. And correction has a pattern. 3 main methods submarines use to reduce drift. 6. Data Triad. 3 drift fixes. Fix number 1. Occasional external fixes. Sometimes the submarine rises to periscope depth to take a GPS or visual reference. It might do this briefly, just enough to update position, then disappear again. This is accurate, but risky, because the surface is where detection tools are strongest, so submarines use this selectively. Fix number 2. Speed over ground measurements. Even without seeing outside, a submarine can measure how fast it is moving relative to the water, and sometimes relative to the sea floor. This improves dead reckoning and constrains INS drift. The details vary by system, but the logic is simple. If you know speed and heading with better accuracy, your position estimate improves. Fix number 3. Bathymetric matching. This one is quietly brilliant. The seafloor is not flat. It has contours. Depth changes with location. If a submarine can measure the depth beneath it as it moves, it can compare that depth signature to known bathymetric maps. If the pattern matches, the sub can say, "We are here." It's navigation by terrain, underwater. Not everywhere has perfect maps. Not every seabed gives clean signatures. But where it works, it's a powerful correction tool that doesn't require surfacing. Now we connect this to the human concept we defined earlier. 7. Dead reckoning. The everyday version of submarine navigation. Dead reckoning is what you do when you leave a place and track your path mentally. I walked straight, then turned left, then went upstairs. A submarine does the same, but with instruments. Heading from gyros, speed from logs, time from clocks. Dead reckoning is not glamorous, but it's fundamental, and it becomes especially important when you can't surface at all, like under ice or in high-risk waters. But dead reckoning inherits the same problem as INS. Errors accumulate. So the system must be designed around one principle. Don't trust one source of truth. Use multiple independent ways to estimate position, then reconcile them. That's what mature navigation looks like. Not one perfect method, but a network of imperfect methods that correct each other. 8. Why shrinkflation-style thinking matters here. There's a deeper idea hiding in submarine navigation. What kills you is not the big, obvious mistake. It's the small, invisible one, repeated long enough. Drift is the submarine version of hidden cost. You don't notice it in the first hour. You notice it when the month feels shorter. Except here, shorter means your map is wrong. That's why correction isn't optional. It's a discipline. And now we do something important for clean thinking. We look at a counterexample. 9. Counterexample, when fixes fail. Not every ocean gives you easy corrections. If you're operating in shallow coastal waters with messy acoustic clatter, over a flat, featureless seabed, or under ice where surfacing is impossible, your correction options shrink. Bathymetry may be less distinctive. External fixes may be too risky or impossible. Currents may push you in ways your models can't fully capture. In these cases, the submarine must behave differently. It may slow down to reduce uncertainty. It may prioritize safer depth margins. It may delay certain maneuvers until confidence is restored. And it will lean harder on redundancy and cross-checking. This is a key lesson. Navigation is not just sensors. It is decision-making under uncertainty. 10. Practical heuristics. How submarines stay accurate. Here are 3 rules that capture the real mindset. Heuristic 1. Reduce drift by design, not by hope. High-quality inertial systems, careful calibration, and redundancy matter because drift is inevitable. If you design as if drift won't happen, the ocean will teach you otherwise. Heuristic 2. Update before you need it. The safest correction is the one you do early, when uncertainty is still small. Waiting until you feel lost means the error has already grown. Heuristic 3. Use more than one kind of truth. External fixes, speed constraints, and terrain matching each fail in different ways. That's why you use them together. The goal is not perfection, it's bounded error. Because a submarine doesn't need to know its position to the centimeter, it needs to know it well enough to stay safe, stay silent, and execute. 11. The invisible map. So when you picture a submarine crossing an ocean, don't imagine it seeing its way forward. Imagine it carrying an invisible map, built from motion sensors, mathematics, occasional reality checks, and the shape of a world it cannot see. In the silent ocean, navigation is not about finding landmarks, it's about controlling error. And that's the deeper theme of this entire series. The ocean punishes certainty. It rewards disciplined estimation. Next Friday, we'll take this lens, this error thinking, and apply it to a real headline concept. When numbers look stable, but the underlying risk is moving. Until then, remember the model. Measure, integrate, correct. Because underwater, the most dangerous place to be is confidently wrong.